sequence problem. And so, of course, there's only one number that will represent the longest common sequence, but there may be more than one string. So actually, we'll be able to find all the string if we want to. And so we were looking at the complexity analysis. These are base cases. Okay. And then this is the general case, worst case analysis. The worst case, these are base cases for worst case, base case for worst case. This is the general worst case. General worst case means we can never find anything. So basically, we're going to explore the entire first string with the first character of the second string removed, but we'll also have to explore the second string with the first string with the first character removed, etc., etc. And then we basically recognize the fact that this is going to be, complexity is going to be exponential in the smaller of the two variables n and m, as shown here. Okay, so this is sort of, and again, this is a table-driven algorithm. What does table-driven mean again? What does table-driven mean? Dynamic is the same thing. That's what does it mean when we have table-driven?
Complexity is dynamic.
Say again?
Complexity is dynamic.
You could put it that way. I mean, the worst case is the worst case, but basically, what it's going to cost you to do a particular operation may depend on when you do it and what was done before. As we saw, if somebody gets Fibonacci of 14 and you want the Fibonacci of 10, what's it going to cost you? What's the complexity in that case? Somebody just called Fibonacci 14, and now I'm calling Fibonacci of 10. What's my 10 cost going to be? It's going to be theta 1. It's going to be unity, right? Constant, unity or constant time. Because we know the table's already, it's just look up, boom, boom. Okay? So for sure, the complexity or the cost of a particular call is going to be dependent upon what came before me. Because what are we doing? We are recording solutions dynamically. Okay, so this is sort of the idea here. So this is, let's take a look at this LCS algorithm. So what we're going to look at is we're going to imagine that we have a two-dimensional array, where the first dimension is basically based on the first string, and the column dimension, or the width, is based on the length of the second string. So in a sense, we could, for any ij intersection, we can take the ith character from the first and intersect it with the jth character of the second, and then we can find out whether they match or not. Okay? So the table ij will correspond to the value of the longest common sequence at that point. Now let's take a look at this implementation. So the precondition here is that x and y are just global strings, so we can access them. And they're going to be indexed to 1 to n, as well as 1 to m, respectively. And LCS returns the length of the longest common sequence. So we are going to pass as parameters into LCS two numbers. So for example, if I pass in a 2 and a 5, what does that mean? Anybody understand? Yeah, so LCS will then return to me what? So if I put a 2-5 for I and j, which correspond to n and m, if I put in 2 and a 5, then LCS will return the longest common substring of what? Well, it will return the longest common substring of the first string limited to the first two characters, with the second string limited to 5 characters. That's what it's going to mean. If both strings have a length of 8, then LCS 8 would return the LCS length. If both n and m are 8 and 8, then 2, 5 will return the length of the longest common sequence, but only of 2 characters from the first string and 5 from the second string, so therefore, what will be the maximum value we can get? 2 will be the maximum. Because if we're going to get those 2 someplace here, that's it. Can't get 3, because you don't have 3. but we could get 1 or we could get 0 if there's no match, or if there's only a single match. Okay. So the table ij will be an intersection of a letter from the first string against the letter of the second string. So we pass in I and j if table ij is empty. So if we haven't written to it before, we're going to check if I is equal to 0 and j is equal to 0. If either one is a 0, we're just going to put a 0 in the table. And the reason we're doing that is because 0 is essentially, if the strings are indexed from 1 to n and 1 to m, then 0 corresponds to an empty string. Therefore, the longest common sequence with no characters considered from one string or the other string is going to be 0. So therefore, if the column or row is 0, then a table ij is equal to 0. You can think of it in a different way. If you take my matrix here, you can simply fill in the first column called 0 column with all zeros, and the first row, row 0, with all zeros. So that's zeros and zeros. Row 0, row 0, column 0. I can't. Column 0, row 0. So I got row 0, column 0. I usually go row column. I outsmarted myself, which is not good. Not good at all. All right. So that's the way it's going to go. Because again, when we fill in those zeros on those vertical and horizontal, we haven't touched any of the letters yet. Okay. So for example, if somebody puts in LCS of 0, 5, that's like saying what's the length of the longest common sequence with an empty string out of the first string and 5 characters. Well, we already know LCS of epsilon and 5 is going to be epsilon. Does that make sense? So else, what do we got here? Else what? Else means that we are not, else means that neither of the strings are empty. These are kind of like base cases. They're base cases, but notice we don't actually return anything. All we do is set a table value. See what I'm saying? So else means that, what does that mean? What does else mean?
If any condition I have to
You're getting too complicated answer. If I equals 0 or j equals 0, okay, else. What else means?
The base case.
Okay, it's not the base case. What does it mean? You want to give me all the answers except for what I'm looking for. Don't tell me what it's not. Tell me what it is.
If there's a match.
No, we're going to check. We're going to check if there's a match. But just hitting this else, what does it mean? It means that this condition is false. What is the simple explanation of this condition being false?
Both the strings contain at least one character.
Thank you. Okay, so that's what it means. So that means that neither of the strings are empty. We have characters to look at. And specifically character I against character j. Now, that could be 1, 1, that could be 1, 5, that could be 5, 3, that could be 5, 5, whatever. So what's the next thing we're going to look at? We're going to say if xi, so both strings have at least one character, so if this character I in the first string x matches the character j in the string y, then we're going to write into table location I, row I, j. I can do much better when I'm facing it. I'm going straight. I'm going in reverse order. I'm trying to satisfy you. I'm going to screw up. Okay, so then we're going to write into table ij. What are we going to write? Well, basically, what do we discover here? We discover that there is a match. And because there's a match, that means whatever came before, we're going to add to it. So we're going to put into this table position 1 plus whatever came before. And why am I adding LCS I minus 1 comma j minus 1?
I mean, they already match.
So let's say for the sake of argument that I is equal to 3 and j, so 3 and j is equal to 5. Now I compare them and I get a true. So I'm going to put into position 3, 5, 1 plus the LCS, what? 2, 4. So now what am I going to do? I'm going to call LCS 2,4. The condition of the base case is false. The condition of xi equal to yi, I have no idea. If they match, then I'm going to put into the table 1 plus. The bottom line is, you understand, this is going to set up a big recursion. So 3 and 5 being equal characters in their respective strings, x3, y5 being equal characters in their respective strings, forces me to evaluate LCS at 2,4. But my question is, why 2,4? What does the position 2,4 indicate? The position 2,4 in the matrix indicates what? If the matrix was completed, 2,4 is what? The number in position 2,4 is what? The longest substring from the first 2 characters of the first string to the first 4 characters of the second string. Let's say that's equal to 1. What does that mean? It means that those 2 characters and those 4 characters, the longest substring we can get out of them is 1. So that means when the 3rd character and the 5th character match, those characters follow the 2 and the 4. So the 3 and the 5 are a match, so they're going to be 1 more than whatever you had up to 2 and 4. Does that make sense? I think it makes sense, right? Now, if they don't, so can somebody tell me why we're subtracting 1 from I and j? And before you answer, I'm going to start giving you another question. Else means that we have characters in each, but they don't match. We're still going to fill in table ij. And table ij is going to equal to the max of LCS I minus 1j with LCS ij minus 1. Okay, so that makes the question a lot more complicated. So again, I'm wondering why we are assigning table ij this way with these indexes and why we're assigning it with these indexes. This is a double recursion here, by the way, because LCS is a recursive function. Is it clear why we're doing this?
No. Yes.
Is it clear? We say no, yes, what do you say?
I say no, I don't know why, I get what it's doing.
I'm ready to take out the markers.
I get what it's doing, but I just don't know why it's doing that.
Okay. You have an intuitive feeling that it's the correct thing, but you don't have an explicit assurance that you fully understand why it's doing it and that you can do it for a different instance of a problem, for example, or a different problem entirely. Okay. So let's say we have let's say this is I and this is j. So obviously we are looking at I and j when they are non-zero indexes. Neither of them is a 0 index. And what I'm going to do is I'm going to highlight the cells, these cells right here. Everyone drawing this so ugly. That's really weird. Okay. I'm just trying to show you that you're in the middle of a matrix. So we're comparing here, okay? Now, let's say this is a match. So that means that character I and X and character J and Y match. But I'm not at the beginning, they're not necessarily the first characters. So that means that this match is going to add 1 to the LCS that we've gotten so far. And since this is character I and J, then I'm going to add it to the maximum value that I got in what positions? Yeah. So if I look at I minus 1 and J minus 1, so there was a value in here. Or there should be a value in here. We can't compute a value in here. So this value in the blue circle is the longest common sequence length for I minus 1 characters in x and j minus 1 in y. I don't know what that number is. It could be 1, could be 0, could be 2, could be 3. But whatever it is, it never looked at the ith character in x and never looked at the jth character in y. But now we're looking at it. And so we know that a match here will add 1 to whatever was here, because these characters, because when you were filling in this number, you did not have any knowledge of the jth character of y and the ith character of x. We did not have knowledge of that, because we didn't look that far ahead yet. So therefore, whatever you got, one shorter on the x and one shorter on the y, by looking at the next characters which happen to match, you're going to get 1 plus this. That's why. Okay, so that explains the matching. So that's why we have table ij is equal to 1 plus LCS of I minus 1, j minus 1. And that's why you notice. So therefore, what we're saying is that cell ij has a dependency on cell I minus 1, j minus 1. There's a dependence on that cell. That's why the arrow is going that way. Now, in case we have a mismatch, so I'll put a x in there. X is going to mean mismatch, so we exit. Can you see that? I think you can see, right? So let's say it's a because sometimes some colors just don't show. Okay, so that's a mismatch. So that means that the I character of x and the j character of y do not match. But I still have to put a number in there, meaning that I want to put in there, because if I am looking at the first I characters of x and the first j characters of y, there is an LCS, regardless of whether I and j match or not. If they don't match, they simply don't increase the LCS, but there is an LCS. I don't know what it is. So the question is, how do I compute that? So, if I look at this cell, this is a cell which is I minus 1 and j. It's possible that I minus 1 character in x and j and y do match. And that should be counted towards the LCS. It's possible. And if it is, then this number is going to reflect that match. So therefore, if I minus 1 to j has a value of, I'm going to say just generally, just n value, then when I move from I minus 1 to j to I to j, then what should I put in here? I'm also going to put an n here. Why? Because adding the ith character is not going to be able to give me anything higher, because the jth character has already matched or not. It's already been compared. You see? I minus 1j, that upper n, now this n, I'll just put a different number in here just so there's a concrete number here. Let's say there's 2. We don't know whether this was a match here or not. If it's a match, then this 2 was more than something before, but if it's not, maybe it's not. But all we know here is that there's a 2 LCS sequence from I minus 1 to j, which means when I add this character, I cannot increase it because j has already been used in computation of this. On the other hand, it's also possible. So in a sense, what I'm looking at here is I'm looking at the first string cut short by 1 character and the full second string up to j. But if I look at this area in here, this index would be I j minus 1. And I j minus 1 is, again, all of the string x, but take 1 character away from y. That also has an LCS value in it. Well, just for the sake of argument, let's say the value here is 1. So let's say this value is 1 here, and this value said was 2 here. Is that possible? Let's think about it. Is that possible? Is it possible that I minus 1j is 2, and ij minus 1 is 1? Is that possible? What do you think? Or is that just crazy? Another way to ask this question is, let's consider a 10-letter word against a 10-letter word. Okay? So we have a 10-letter word. Okay, 10 is so much. Let's do 5. Okay, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And we'll just call them X and Y since those are our favorite names so far for strings. And so, and for the sake of argument, let's make this I. And let's call this J. Okay. So our comparison basically is going to be this character against this character. And the cool thing about my example is that it's entirely possible that individually, independently, this definitely could be a 2, and independently, this definitely could be a 1, for sure. Okay, because this one represents the entire string, all 3 of these characters, right? Being compared to what? All 3 of these, guys, I'm talking about the 1 here, right? So that means I is taking consideration to 1, 2, 3. And J, what's the value of J? J is going up to J minus 1. We're only going to consider the first 3. Is it possible that the LCS between, so we're looking here, is it possible that the LCS between these 3 and these 3 is 1? Can you make this scenario up? Of course you can. But you understand that's possible. So it's possible that this is equal to 1. Now what I want to ask you is it possible that this is equal to 1 and the other one is equal to 2 at the same time? That's what I'm asking you. So the second part of the question, so I will kind of highlight these again. So this is going to be here and here, and we're saying that's equal to 1. I don't know if you can see the colors here. I'm trying to do it a little bit different. And so now this one basically is talking about I minus 1, which means that we're talking about this, but then we're talking about that. So simultaneously, the blue substrings have to have an LCS of 1, and the yellow substrings, if you will, have to have an LCS of 2. Is that possible? Is that possible? Well, what do you think? Okay, it is possible. Actually, it is possible. So let's see what could happen. So basically, let's look at the blue one. The blue one has a 1. So for instance, what we might have, let's say, the only character in the blue string, let's say the only character in the blue string that matched was, let's say, this one matched to this one. Or let's say, we're looking at the blue one. So that second character has to do, where does the second character have to be? So the second one is the yellow one. In the yellow one, we're adding this one, which means that this one has to produce a match. So where is this yellow one going to match to? So could it match here?
Yeah.
Okay. And where's the second one? The second one could be anywhere. So the second one has to be here. To this, or this. Right? Correct?
Yeah.
So let's say it's going to be this to this. That's 2 for the yellow. Now is that consistent? That's also consistent with the blue, right? Because this one is still going to be this value. The blue value has to be at least 1 because this is a 1. But it's possible that we don't have a match here, right? And we haven't seen this character yet at all. So this is possible. Okay, so if it's possible, what value should go into position ij? 2. And the reason for that is because The reason for that is because we can consider using j and using I with either j with I minus 1 or I minus 1 with a full j. So therefore the value here will be the bigger of the two. If it's not a match. If it's not a match. Now, if ij is a match, what do we do? No. If ij is a match, then we're going to have 1 plus, we cannot use this because this is already used j. We cannot use this because it's already used I, and we're matching I to j. So we have to back up 1 character from each string. And that means we got to go up 1 for I, and to the left 1 for this string j. So that's why this value, if it's a match, we're going to get 1 plus this. But if it's not a match, we're going to get the max of these two. That's the idea. So to simplify things now, go back to what we see here is that the value of ij is a dependency of 3 other cells. And we call this relationship, what we talked about yesterday, a topological ordering. T-O-P-O-L-O-G-I-C-A-L, topological ordering. And topological ordering basically is when you can draw arrows in a one-dimensional vector, a two-dimensional matrix, or a three-dimensional space between cells, intersections of cells. Now, looking at that right then and there should give you an idea, some interesting idea of how to design an algorithm for this problem that's going to do better than exponential in m or n, as we looked at in the worst case. Because we could always have a worst case. Worst case can be generated everywhere, but the question is, what's the complexity of the worst case? So far, we thought it was going to be exponential, but maybe we can do better than that. Maybe we can do better than that. So, I want you to look at this algorithm and tell me how we can turn this horribly, badly implemented algorithm that's so beautiful into something much more efficient and table-driven. So if I put in 5 and 5, this will store 5 and 5, but not before it has to evaluate 4 and 4. So 4 and 4 goes in. If they are not equal, I will score 4 and 4, but not before I evaluate 3 and 4, and 4 and 3. But not before I evaluate, you understand what I'm saying? It's going to be nasty. It's going to be a lot of recursion. That recursion is going to get us right back to that exponential complexity. Can you think about how to improve this algorithm in a simple way? No. We don't want a tree. We almost have everything there. It's a funny thing. It's like this algorithm is almost improved. What we want is okay. Well, okay, let's go ahead and move ahead and see what we can see. So this is sort of, if we're going to use this algorithm, we have this kind of sort of a recursive idea. So let's say if the first string is x, acorn, and the second one is car, and essentially this is 5, this is 3, LCS of 5, 3, and you can see how the recursion is going to happen. And so what's going to happen here, this thing is going to explode exponentially with n and m. So how can we stop? So what I want you to notice specifically is why is this exploding exponentially? Think about Fibonacci, why that was exploding exponentially, and how we're able to circumvent that explosion exponentially to make it much more efficient, to make it linear. How can it make that linear? What tells you that this is bad? That's it. So we are computing the same things over and over again. Like in Fibonacci of 7, we had to compute Fibonacci of 6. But I know that when I computed Fibonacci of 6, I needed 5 and 4, which means 5 was computed, and then I go to the right-hand side of 7, I have to do 5. But it's already been done, so I'm repeating it. So what's the solution? How can we take advantage of what we're seeing here? Store the value, always. And whenever you are asked to look at a value of ij, the first thing you do is look in the table. If it's in there, you're done. If it's not in there, you have to start the process of evaluating it. But you can see that here we're going to look at 2 and 1. Done here, done here, done here, 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 here. We're just repeating our work. And this is only going to get worse if I have bigger strings. Okay, so that's a good idea. So you can see that our topological ordering has a dependency that is shown here. Every cell in the matrix is dependent only on the cell above it, the one to the left of it, and the one above it. But we know that the first row, row 0, is all zeros. And we know that column 0 is all zeros, because they represent epsilons, empty strings. So basically, we can see that LCS ij depends only on the neighbors. This is the diagonal neighbor, okay? This is the neighbor, which is going to be to the left, and this is the neighbor that's going to be above. So would you agree that I can fill this in with zeros? Or better yet, rather than filling in with zeros, let's imagine there's another row here, zeros and zeros, which gives us room for a 4-letter word and a 4-letter word. So if we put zeros outside here and outside, so let's put all zeros here. So this is going to be row 1, row 2, row 3, row 4, column 1, 2, 3, 4. So what's the dependency of 1, 1? 1, 1 depends on what? Zero, zero. 1, 0. 0, 1. So what's going to go into this box? 1 or 0. When will a 1 go in here? Only when there's a match on 1 against 1. First character against first character. That's a 1. Otherwise, it'll be a 0. How about this one? Can I fill in this one next? That's comparing character 1 against character 2. I can. So let's say this is a match. Let's say it's a match. Let's say this is a 1. Let's say this is a match. And this is a match. What's going to go in here?